Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, greetings to all those that will be watching this video at the time that it's posted, and those present. Today what we're going to do, grade 12s, is we're going to have a look at the grade 12 physical science chemistry paper. It's paper 2 of last year's matrics, November 2020. And we're going to see exactly what those children nationwide were sweating, crying, and having headaches and pains in their fingers for. We're going to see if the questions was as bad as they portrayed it to be. Okay, let's go have a look. Okay, so of course we'll start with section B, because section 1 is multiple choice, and multiple choice, well, we know how to handle multiple choice. Maybe we'll go through that at the end just for some tips and tricks. Okay, but some instructions quickly. The chemistry instructions are sort of a little different, because yes, there are calculations, of course, but they're slightly different. Besides the normal write your exam number and whatever on the and center number in the answer book and blah blah blah. It will state obviously the name of the number of questions, but of course some important ones like rule number 5 or instruction number 5, leave one line between two sub questions. So question 2.1, then you leave a line, and then you start question 2.2. Okay, and also the second most important, if not the first most important, is always look for how many decimal places. You must round off your numerical answers. Okay, such as this one, which they want you to keep to a minimum of 2. Okay, and so basically just 2 decimal places as well. Okay, and it's chemistry, so they also want you to keep your motivations also pretty brief. Okay, pretty brief as possible. You don't need to write like an essay for an answer. Okay, so even though we've been writing chemistry papers for what, 3 years now, grade 10, 11, and 12, we must still pay attention to these question papers as well. To these instructions in the question paper. So I think a good place to begin is, because we haven't done it in a while, is organic chemistry, which is question 2. And we'll start here, and maybe we'll jump around in the paper, you know, and because there's usually about 4 or 5 organic chemistry paper questions, because it's such a large topic. But we'll jump around maybe from start to finish, just to see if we can cut through some sections, make it go a little faster. Also trick the brain into always being ready, because we don't want to train the brain for patterns. You know, we want to shock it a little bit. And it's a Saturday morning at the moment, so we're definitely going to need to shock the brain and wake it up a little bit. So we'll start with question 2. Now the instruction here is that the letters A to E in the table, they represent 5 organic compounds. Okay, as we can see there, we've got structural formula for A and C. We've got the name, the IUPAC name for D and E, and it looks like a molecular formula for B. Okay, let's see if I do that. Okay, that's fine. So we can do questions 2.1 and 2.2, and then we'll scroll down to do 2.3 at the end, and that's 12 marks, and then we'll mark the question after that. So for now, just to wake up the brain a little bit on this early Saturday morning, 2.1 and 2.2 first, please. Okay, so let's have a look for 2.1. They say for compound D, which we have here, pentan 2-one, write down 2.1.1, the homologous series to which it belongs to. That's a fairly easy question. Okay, this is paper 2, November 2020. I don't actually know why I always hit this. I only hit the first slide. Anyway, it doesn't really matter. Question 2. 2.1.1, and that would be ketones. Okay, because there we go, own, it's in the name, right? All in the name. Okay, so that was a very simple one, ketones, and the own there gave it away. 2.1.2, the IUPAC name of the functional isomer, also of compound D. Okay, now what helps with that, if you want to work out an isomer, you could draw the structural formula in pencil, like on the side here maybe, just quick structural formula in pencil, just to maybe see, okay, great, how would this look? Because I'm more of a visual person, so if I can't picture it in my mind too well, I would take the not so nice picture, or not so well drawn, formulated picture in my brain and take it out and put it on paper, and then paper it's a little more clearer. All right, for example, that's the type of learner I am. So the functional isomer of pentan 2-one, okay, would be pentanol. Okay, that was pretty easy. Okay, 2.2.1, which is the next one. Okay, it says write down the IUPAC name of compound A. So let's have a look here. We've got 1, 2, 3, 4, 5, 6. Okay, and let's see. Here we go. We got 1, 2. Okay, and here we got 1, 2. Okay, cool. So what we want to do is we want to take care of the position, right, or the positioning of the methyls first. In the name though, okay, we are going to put the halogen first in the name, okay, but we want to make sure that when in our name, okay, that we don't want to start counting here and make it 2-bromo, all right, and then we have, so if that's 2-bromo, then we have 1, 2, 3, 4 dimethyl. We don't want that. We want to rather make sure that the methyl position are closer in the chain than the halogen. Okay, so how we name this is, we know that's 1, 2, 3, 4, 5, 6. We know it's hexane because also it's a straight carbon chain, single bond, so we know it belongs to alkane, so we know it's hexane. Okay, we see the positions of the methyl. It is 2-methyl, so it's going to be dimethyl. And now we just take into account, or we consider, the positionings of the methyls and the bromine. So the correct name is actually 5-bromo 2,3 dash dimethyl, and this is one word, hexane. So there's no space in between the dimethyl and the hexane. It's dimethyl hexane. Okay, that's actually the correct name of compound A. Okay, 2.2.2, to give the structural formula of compound E. Okay, so this one is, you have to be careful with this one because we've got 4-methyl, so we've got 1-methyl, 4-methyl, pent 2-ine. So we know it's an alkyne, and they're telling you the position of the triple bond must be on the second carbon, okay, or between the second and third carbon. So let's go over here. It's pent, so it's 5. So 1. Oh, wait, hold on. I'm just gonna draw a straight chain for now before I add in the other ones. 2, 3, 4. All right. Okay. Cool. Just take care of this one. There we go. Okay. So how I always draw it, I always add in all my just the branches first, and then I add in the hydrogens afterwards just to get it right. Okay. So. Okay, I'm going to start counting from this side. So I'm going to go 1 and 2. So I'm going to put the second one there. Okay, so between the second and third carbon, there's my positioning of my triple bond. Okay, I'm just going to circle it for you guys. And so if that's the second, between the second and third is my triple bond. So that's 1, 2, and this is the fourth one. So here's my methyl at the end here, and now you can just add in the hydrogens. Okay, obviously yours will be better drawn with the ruler and everything. There we go, nothing on between the middle here. There we go. Okay, and that's how it will look. Okay, I don't need to actually add in this green line. You can all see where it is, so I'm just going to remove it. Okay, there you go. Awesome. And that's how it should look. Cool. I'm going to go ahead and say that if you started counting 1, 2, and fourth one was over here, I think it will still look correct. I don't think it'll be any of a problem. This is just how I decided to draw how to draw it, because remember, with organic chemistry, when it comes to structural formula, it matters from where you count by when it comes to making the chain less longer than what it actually looks like. Okay, so we wouldn't want to say 2-methyl 4, you know, rather 4-methyl pent-2-ine. So could have written it here as well, wouldn't have really mattered. All right, I think that's the first part, and we're almost done. Let's just have a look at 2.3. I think 2.3.1 or 2.3, they told you that about compound B, C3H8O. It's a primary alcohol, and you have to write down the meaning of the term primary alcohol. So there's a lot of ways that you can obviously write down this definition. A couple of them being that the carbon atom bonded to the hydroxyl group, okay, is bonded to one other carbon atom, okay, or the hydroxyl group, which is your OH, is bonded to a carbon atom which is bonded to 2 other hydrogen atoms, okay, or the hydroxyl group, or the OH, is bonded to a primary carbon atom, or the first carbon atom. See, many ways that you can obviously word this, but I'm going to word it for the first definition, that the C atom, which is the carbon atom, you don't need to write out the full word, the C atom bonded to the hydroxyl group, so that's the carbon that has the OH bonded to it, hydroxyl. That's what OH is called. It's called hydroxyl group. All right. That carbon is bonded to only one other carbon atom, or C atom rather. Okay. That's a good enough definition. Okay. Awesome. 2.3.2. All right, let's check here. Compound B reacts with another organic compound X, which is obviously not present in the table there, but it forms compound C. Okay, so here we got compound C here. We can see it. Excuse the pun. They say, write down the type of reaction that takes place. Okay, well, we can look at the group and see we've got a carbon bonded to a single bond to an oxygen that is singly bonded to another carbon to a double bonded oxygen. So we can definitely recognize this functional group to know what that this compound homologous series belongs to. So we can definitely tell the type of reaction that takes place, and it is esterification. Okay, the process of forming an ester. The last one, 2.3.3, I think they asked for the name of compound X. So in other words, if which is an alcohol plus what gives us an ester, we know what that is. We know it is a it's a carboxylic acid. All right, so we need to just determine what was the name of the carboxylic acid, right? What was the name of it? So let's look here. So we've got 1, 2, 3. So that's part of the alcohol, and we start counting from this carbon. 1, 2, 3, 4. So we see it's 4 carbons. So we know 4 carbons in a straight chain, if it was an alkane, would be butane, but because it's a carboxylic acid, we know the name of it, therefore it needs to be butanoic acid. Okay, and that wrapped up 12 marks of juicy goodness. All right, not bad, pretty straightforward. I would say this little table of organic compounds, pretty straightforward. Okay, question 7. We're jumping to question 7. It's the acids and base section. in the question paper. And it starts off with 7.1 saying ethanoic acid CH3COOH is an ingredient of household vinegar. 7.1.1, is ethanoic acid a weak acid or a strong acid? Give a reason for your answer. Well, guys, anybody like to comment? Anybody like to comment? Is it a weak or strong acid? What say the people? Yes, it is indeed a weak acid. So let's write it down here. All right, it's a weak acid. Okay, why is it a weak acid? Okay, why? Who knows why? What say the people? Okay, weak it is correct. Does not fully ionize in water. Yes, it does. I would say, yeah, actually it's right. I wouldn't actually put it in any other way, right? It does not. Let me just write it with a full sentence. It does not fully ionize in water. Okay. There is another option, actually, maybe that someone else could have put it. It says that it dissociates incompletely in water, okay? Or you could have said it does not completely ionize in water. You wanted to use completely instead of fully, okay? But basically, they're both saying the same thing, is that it does not fully ionize in water. That's why it is a weak acid, okay? Now, I believe there was 7.1.2. Let's go find out that question. An ethanoic acid solution has a pH of 3,85 at 25 degrees Celsius. Calculate the concentration of the hydronium ions H3 plus in aqueous in the solution. All right, well, that should be basic. It should be pH formula is equal to negative log, all right, the concentration brackets H3O plus, like that, okay? All right, so we add the pH here, substitute 3,85 equal to negative log. There we go, H3O plus, okay? I think we've got to divide both sides by -1, so we end up with minus 3,85 is equal to log concentration H3O plus. Now what we need to do here is we need to actually press second function on our calculator and then press log. So we'll end up with the concentration of hydronium ions equaling to 10 to the power of minus 3,85, and therefore the concentration of hydronium ions, H3O plus, if we put that in on our calculator, will equal, I'm just going to do it quickly, minus 3,85, end up with 1 to 2 decimal places, 1,41 times 10 to the power of minus 4, and that's concentration, so it is mole per decimeter cube. Okay, you don't have to put a full stop at the end there. I just made a mistake, I did it. Okay. Nice little question there. Okay, that was 3 marks. Awesome. Okay, now they say sodium ethanoate, CH3COO, Na in aqueous, forms when ethanoic acid reacts with sodium hydroxide. 7.1.3, will the pH of sodium ethanoate solution be greater than 7, or will it be less than 7 or equal to 7? Okay, now let's have a look here. 7.1.4 says give the reason. Well, we are reacting sorry, ethanoic acid, we are reacting that with sodium, all right, hydroxide. So I think the formula for that, because it's in aqueous solution, so I might need a new level thingy for that. If I think about it, it should be CH3COONA in aqueous plus water, which is a liquid. That should be a reversible reaction, I think, yeah. CH3COOH, which is ethanoic acid here, plus NaOH in aqueous solution. Okay. Cool. So basically, obviously this would be the forward reaction, all right, going this way. And then if you react that further with water, you'd get back to that. Okay, so this looks like that's what's happening there. So if I look at it here, this side here, which is the ethanoic acid reacting with the sodium hydroxide, there's a presence of hydroxide here, okay, which is this is a very strong base, okay, as it's used in a lot of reactions, okay. And then you get obviously the sodium, sorry, what's that name again? Just go back. I forgot the name of it. Oh, sorry, my WhatsApp web's opening by accident. Sorry, I clicked on it. Sodium ethanoate. Sorry, there we go. That's the word. Sodium ethanoate plus water, of course. So for my answer for 7.1.3, because I'm seeing that position of a strong base, presence of a strong base. Sorry, I'm going to say greater than, and my reasoning is going to be for 7.1.4. Just based off the above equation, is that due to the formation of hydroxide, all right, which is obviously OH to the minus there, or we can see it forms in there, OH, okay. This would basically mean, therefore, if we had to specified, due to the formation of hydroxide, that's why the pH is going to be greater than 7. The pH will be greater than 7 because there's the formation of an hydroxide, okay, in the reverse reaction, okay. So, and in the forward reaction, it plays a part, okay, forms water. So the pH of CH3CONA is definitely going to be greater than CH3COOH. Okay, cool. Now 7.2, we're continuing with household vinegar. It contains 4,52% ethanoic acid by volume. A 1,2 gram impure sample of calcium carbonate is added to 25 cubic centimeters of household vinegar. On completion of the reaction, the excess ethanoic acid in the household vinegar is neutralized by 14,5 centimeters cubed of a sodium hydroxide solution of concentration 1 mole per decimeter cubed. The balanced equation for the reaction is as follows. Wow, there was a lot to actually read through before we got to that reaction. Okay, let's make sure we track all those numbers and all the volumes and all the concentrations, please, of all those substances. It's nice to track it just on the right-hand side of your answer script in pencil, if you wish to erase it. Otherwise, in pen can also be fine, just so you can jot down everything you need for the question. Now, they've given us the balanced equation there. Everything's in a ratio of 1:1. Calculate the number of moles of unreacted ethanoic acid. Okay, cool. So let's see. I have a concentration for sodium hydroxide. I also have the percentage composition of ethanoic acid, apparently. I have the volume of household vinegar, though. Excess ethanoic acid, vinegar is neutralized by 14,5 centimeters cubed of sodium hydroxide. So also have the volume of the base as well. And I need the volume of unreacted ethanoic acid. Okay. Well, let me find out what is the number of moles of sodium hydroxide since I've got a volume and a concentration. So let's come and let's take the number of moles of NaOH to be specific, or you could have written it like this in brackets so that we know exactly the number of which moles we're calculating. That's equal to the concentration times the volume, which is equal to, of course, the 1 mole per decimeter cubed multiplied by the 14,5 centimeters cubed must be converted to decimeters cubed, so that's 0,0145. So that means the number of moles that we have is 0,0145 mole of sodium hydroxide, okay, in the reaction that reacts with the ethanoic acid. Now we know they are in the same mole ratio. Okay, number of moles, they're the same mole ratio. So the number of moles of the unreacted CH3COOH, okay, in the reaction, which is diluted, will be equal to the same amount of moles as sodium hydroxide, therefore equaling to 0,0145 mole. That's 3 marks. Okay, because the question was calculate the number of moles of the unreacted ethanoic acid. All done. Now 7.2.2. 7.2.2, calcium carbonate reacts with ethanoic acid according to the following balanced equation. Okay. Calculate the percentage of calcium carbonate in the impure sample if 1 cubic centimeter of household vinegar has a mass of 1 gram. Okay. Well, first things first would be probably to find out, because they told us at the beginning that household vinegar contains 4,52% of ethanoic acid. So what we should do is probably find out the mass of ethanoic acid that is present. Okay. Now, that's not the only thing they told us. They said that household vinegar contains 4,52% ethanoic acid. And they said that a 1,2 gram of impure calcium carbonate is added to 25 cubic centimeters, all right, of household vinegar. Okay, so we want to find out what is the mass first, okay, of the ethanoic acid present. So in order to do that, for 7.2.2, let's calculate the mass of CH3. So let's go MC. Let's make that bracket a bit nicer. CH3COOH. Okay, so we've got 4,52%, so that's over 100. And we're going to times it by the volume to find out the mass of it in that volume. So times it by the 25. All right, that should give us 1,13 grams. Okay, on your calculator, should give you 1,13 grams, or 1,13 grams rather. Okay, now that you got that, let's calculate the amount of moles. All right, because the molar mass of CH3COH, the molar mass is 60 grams per mole. Okay, if you don't believe me, it's 12. Okay, plus 3 for the hydrogen there, H3, plus another 12, plus 16, that's 32 plus 1. Yeah, 60 on the dot. Okay, so the number of moles of CH3COOH should give us the mass, which is, well, let's write the formula first. Okay, that should give us 1,13 divided by 60. Okay, and that should equal, let's see, 1.13 divided by 60. Ah, it's quite a big number. 0,0188, I'm going to say 3 mole. The reason why I'm writing it out like that is because that's not my final answer. So remember, the instruction was my final answer must be kept to a minimum of 2. So I don't have to keep this answer to a minimum of 2 because it's not my final. Now, in order to find out now the amount of moles that reacted, right? Remember, we have calculated the moles present in 25 cubic centimeters. We also calculated the amount of moles in the previous question was unreacted. So then what was the how many moles actually reacted? So moles of CH3COOH that reacted is equal to our answer 0,01883 mole minus 0,0145, 0,0043 moles reacted. Okay, now remember, for calcium carbonate in the question, we've got calcium carbonate to CH3COOH, we've got a ratio of 1:2. So if we want to find out the number of moles of calcium carbonate, it's obviously going to be this amount of moles divided by 2 times 1. Okay, so it's basically a half, if you think about it. So the amount of moles of Ca, let me put the bracket properly, sorry, CaCO3, okay, and that is equal to half the mole of the ethanoic acid that reacted. So this one, okay, not this moles or the previous or this mole, it's this one over here. Okay, so basically we're going to take 0.5, which is a half, times 0.0043, and then that should give us amount of moles of calcium carbonate to be about 0.00217 mole. Okay, now we're keeping these long decimals because we're going to need them before we round off to our final answer. Okay, all right, cool. So we got that, and now we just need to find out now what is the mass. Okay, so we come over here, we take that answer. We take now, what is the, there we go. What is the mass of CaCO3? That's going to equal to, of course, the mole times the molar mass. So we got the mole to be 0.00217. Molar mass of calcium carbonate is 100, and that's going to equal to 0.217 grams. Now that we do that, if you want to find out the percentage calcium carbonate, okay, that's equal now to the number of moles, 2.17. We're going to divide that by the mass, which is 1.2 grams. That said it reacted. We're going to multiply that by 100 to get percentage. And once we do that, we should get rounded off to about 18.08%. Okay, as the question asked, calculate the percentage calcium carbonate in the impure sample. So the sample of impure had a mass of 1.2 grams. Okay, calculate that if 1 cubic centimeter of household vinegar has a mass of 1 gram. Okay, so that's why we kept that answer in 25 cubic centimeters while we used 25, because 1 cubic centimeter was equal to 1 gram. So we had to pay attention to that and not convert to decimeters cubed. Alright, we're just going to jump to question 8 quickly. Question 8 is the start of the redox section, or should I say in grade 12 we call it electrochemistry. Okay, question 8 and 9, both electrochemistry questions. But question 8 usually deals with your galvanic cell, okay, which we do see here. Okay, it's not probably one of the most favored or favorable galvanic cells to have a look at, but hey, we'll take it because it's our galvanic cell, and I'm sure we know it pretty well as well. What I'm going to do before we begin there, I'm just going to rock on and get me my table of standard reduction potentials, because I know I'm going to need that. So I'm just going to put it up here on my chair here from my one of the textbooks that we use for grade 12. Also open it to the back so I can find it. There we go. Lovely stuff. Alrighty. So the electrochemical cell in question 8 illustrated below is set up under standard conditions. 8.1. Alright, 8.1 says the component X completes the circuit in the cell. Alright, state one other function of component X. Now I did mention this to you all throughout the year, that it's not good enough to just remember the easiest answer for component X. Okay, that I don't think they've asked us to name what component X is, so we can name it now for the purpose of reminding ourselves that it is the salt bridge. So we cannot just remember the salt bridge. Okay, it completes the circuit. Oh yeah, cool. No, that's not good enough. We need to know more than one, because they've actually, what happens if you only memorize that it completes the circuit? Yeah, they've given you that is the truth. They've given that to you. You can't state that as an answer, so there you go. You lose 1 mark. You're already on -1, so you've got 13 marks left to make up. Right? You don't want to put yourself in that predicament. Okay, so another function of component X. Okay, for question 8. Anybody? I actually meant to ask that as a question. I realized I didn't. Besides completing the circuit?
It ensures electrical neutrality in the cell.
Very good. Ensures. Sorry, Zulekha, did you say electron or electrical?
I see electrical.
Electrical. Okay. Electrical neutrality. Neutrality. There we go. In the cell. There we go. Awesome. Okay, that is one other function. Or what we also could have said as the other one, because there are three, it provides. Could also say ensure if you want to, but it provides a path for movement, or for the movement of ions, or provides a path for ions to move. Okay, obviously between the two electrodes. Okay, so either one you would have gotten your mark. Okay, 8.2, another definition, asks us to define the term anode, okay, which I'll define for everybody right now. 8.2, anode is the electrode, of course, where oxidation takes place. Okay, another way to say this is also the electrode where electrons are also lost. Okay, either one is fine. Okay, just correct, because I wrote that like I was Speed Racer. Okay, here we go, electrode. Okay, I think we're on 8.3. All right, identify the anode in the above cell. Can anybody identify the anode in the above cell? You can just give me the name either in molecular formula, or you can give me the name as in the actual chemical name. They're not specific. So the anode in the above cell. Anybody? Let's have a look in the chat. So Mg, yes, Mg magnesium. All right, excellent there. Thank you so much. Mg, or you could have written magnesium. Okay, cool. How would we have determined whether or not that was? Well, we could have gone to our standard table of reduction potentials, and we could have found the reaction for magnesium, and that has, of course, a minus 2,36 value there, as the EMF value there, minus 2,36. And then if we move to the other question, we got a platinum electrode, but we got hydrogen gas coming in there. And if we go find the hydrogen one, obviously that has 1 of 0. So we definitely know that the one that was more negative is our anode. Okay, let's write down 8.4.1 quickly, and let's go find out that question. All right. Write down the reduction half reaction that take place in the cell. Well, I kind of gave that away now, because the other one, judging by what forms in the aqueous solution there, that will determine what is the other chemical, or the other substance. It is hydrogen, so we just write down the reduction one, which is in the middle and has a EMF of 0, so it's just 2H plus 2 electrons, and obviously that goes to just, H2 gas. Okay, that's the reduction half reaction. I think I can fit 8.4.2 in here. Let's have a look. The name or formula of the reducing agent in the cell. Now, the reducing agent, of course, is the substance that basically gets oxidized, which is the same as the substance at the anode. So it's magnesium. So name or formula, so you could have written down magnesium or Mg. Okay, whichever one you decided to go best, or best suited it. Okay, All right, let's find out the next question before we change layers. All right, they asked for cell potential, I think, at 8.5. Calculate the initial voltmeter reading of the cell under standard conditions. Okay, so we know exactly the two substances that we are working with. Okay, so we know that the cell potential, which is the EMF of the cell, okay, is equal, of course, to the anode. Sorry, it's cathode minus anode. There you go. Or you could have said reduction minus oxidation, same thing, different flavor. So we know that the cell potential there, or the voltmeter reading of hydrogen, is 0 minus, and we know that magnesium is minus 2,36. We find that on the table of standard reduction potentials. I used table 2A, but you could have used table, sorry, not 2A, 4A. You could have used table 4B. I've said this multiple times in previous lessons, but back when I was in school, I learned how to use both, depending on what I was looking for. Some people just get acquainted with one. So we know that's going to end up to be a positive, so our voltmeter reading under standard conditions for this cell is obviously 2,36 volts, which is 0 plus 2,36. Minus times a minus is a positive. That goes without saying, but I said it anyway. Okay. Now this is the half cell magnesium, Mg2 plus half cell is now replaced by copper half cell. All right, Cu2 plus. It is found that the direction of the flow changes. Okay, fully explain why there is a change in direction of electron flow by referring to relative strengths of the reducing agents involved. Well, the first thing to do to answer this question, again, is to have a look on the table of standard reduction potentials. Where is the copper half reaction? But it's the copper 2 plus half reaction. Okay, so I'm going to look on table 4A first, and I find it easier in the more top half of the table. Obviously it's above 0, and that initial that EMF value, voltmeter reading there, is positive 0,34. Hydrogen stays the same, that's at 0. So the copper half cell, or the copper half reaction, gives me a more positive value, okay, for the potential. So the rule is, if both of your values are positive, the one that's more positive will be your reduction, and the one that's less positive will be your oxidation. So in other words, now hydrogen is going to be oxidized, and no longer, and copper is going to be reduced. All right, so hydrogen is going to be oxidized and copper is going to be reduced. Okay, so in our explanation for 8.6, okay, we can say that hydrogen, all right, H2, is a stronger reducing agent. Now, reducing agent works with oxidation, okay, and oxidizing agent works with reduction. Okay, H2 is a stronger reducing agent, okay, than copper, and therefore the Cu2 plus ions are reduced. All right, the Cu2 plus ions are reduced, or you could have said that therefore the hydrogen, or H2, is oxidized, okay? Specifying that electrons flow from hydrogen, so from H2 to copper, Cu. They are flowing now the opposite direction, okay? Because hydrogen is being oxidized, okay? The Cu2 plus ions, they are now being reduced. Okay, very easy explanation. And if we understood our table of standard reduction potentials, we would have seen that. It would have been quite easy to put that down. And that was for 3 marks. So Mark probably would have come around mentioning that it's a stronger reducing agent than, and mentioning the substance, so copper, and saying therefore which ions would either be reduced or oxidized. Okay, either one. Question 9, carrying on with the electrochemistry. A simplified diagram below represents an electrolytic cell used to electroplate copper, or a copper coin rather, with silver. Okay, so there we go. We got the copper coin, electrolyte, silver electrode, and of course the power source, which looks like it's a battery of some sort. Okay, let's see. Define the term electrolysis. So, defining the term electrolysis, I'll do all the definitions because, you know, they can be a little bit of a mouthful. Okay, so I think there's about more than one way that we can define it though, but I'm going to give you one that I know. Learn the one that best suits you, that makes you better understand what the process is all about. But electrolysis is, for me, and the definition that always helps me understand what it is, it's first of all a chemical process. We rather say in which electrical energy is converted into chemical energy. Can I fit energy here? Yeah, my energy can fit in there. There we go. Awesome. Cool. Okay, that's the whole process of or the definition of electrolysis. Okay, it's a chemical process in which electrical energy coming from the power source is converted into chemical energy. With the galvanic cells, the opposite. Okay, chemical energy is converted into electrical energy. That's why we have a voltmeter there, picking up, right, a voltage, which is basically electrical energy. Defined. But that's from physics. Let's leave that alone. Let's focus on electrolytic cells. Which component in the diagram indicates that this is an electrolytic cell? Any takers for that one? Quick, one more question there. Which component? In the diagram? The cell or the battery? Okay. Okay, I'll say the battery that we see there. This component here indicates that it is indeed a electrolytic cell. If you said power source as well, also would have been acceptable, because that's what a battery is, or a cell is. It is a power source after all. So, good vibes. 9.3, write down the name or formula of the electrolyte that is usually used. All right, especially we can take it from the name here. We are trying to coat a copper coin with silver. Okay, so probably a good name or formula for electrolyte. Let's hear. Anybody would like to go and take this question? What's a good name or formula for an electrolyte to use here? I'll give you a hint. It has got silver in it. For 9.3, name or formula? Probably because we can't really type out in physics formulae here on keyboards or whatever, so we can maybe just say the name. I know we know this, guys. I know we know this. We've done this. We spent a bit of time on this one. What's a good electrolyte? Ah, okay, cool. Someone managed to get the formula in. Okay, for 9.3. AgNO3, all right, which is by name silver nitrate. Okay, that's a good electrolyte. Okay, basically any electrolyte that had silver in, okay, would have been a good answer. Okay, silver ethanoate, silver fluoride, all right, silver perchlorate, okay, which is AgClO4. Okay. But, you know, I always say to students, you don't need to reinvent the wheel. You don't need to show, show off in your answers sometimes, Sometimes you can, but why? Okay? It's question 9. It's nearing the end of your exam period, okay? Your brain doesn't feel like showing off. Your brain's tired. Your brain, you want to get out, all right? You just want to leave the hall. You want to go home. You want to rest. Your brain has been working overtime. So, point of the matter is, write down the most common one, silver nitrate, AgNO3, easy vibes, okay? Or silver fluoride, AgF, also would have worked out for you, okay? But the silver perchlorate, if you remembered that, then good on you. But what I'm saying is you don't need to really go hectically. It's any one of those could have been a good answer. But silver nitrate, the most common, fairly easy. Go for that one. 9.4. How will the concentration of the electrolyte change during electroplating? Choose from increases, decreases, or remains the same. Let's read that again. How will the concentration of the electrolyte, okay, right, the solution, all right, how will that change during electroplating? Because we are coating the copper coin with silver, all right, from the silver electrode, okay? Write down or choose from increases, decreases, or remains the same. Give a reason for your answer. Well, I'll open up this question to everybody here. Is it increases, decreases, or remains the same? The concentration of the electrolyte. Does it increase, decrease, or does it remain the same? If you took a guess? Oh, and my bad, but someone other than Zuleika. Shame. I think Zuleika's working a bit overtime, yeah? Come on, there's other people in the class as well. So Zuleika, take a break. Take a break. Rest easy. Anyone else? Increases, decreases, or remains the same? 9.4 is quite a mind. I think the term is correct. I used it off air now, but it's a very mind bamboozlement question. It's meant to actually mess around with your head. Your head will second guess itself, and you'll go back and forth, back and forth, back and forth. This answer, that answer, but this, but that. It's designed to do that. But if you go there in your head whilst you're writing this paper, you're going to panic, and you're probably not going to choose the correct answer. So it's best to divert to remaining calm, and let's go with logic. Okay. We already have a silver electrode in our cell. All right? Electrolytic cell. We have already silver in our solution, in our electrolyte. So basically what's happening is that we're going to coat the copper coin with the silver. So in other words, the silver is going to, from the electrode, is obviously going to be oxidized, and it's going to go all the way onto the copper coin. All right? So it's going somewhere. Okay? Now the minute it goes somewhere, it's no longer present in the solution. Correct? It's no longer present in the solution. Okay? Therefore, by that logic, because the silver here is going somewhere, it's coming out of the solution. It's not adding to the solution, neither is it taking anything away from it. All right? Even so, if the silver from the electrolyte even had to go to the copper plate, the silver from the electrode would still be oxidized in any case and bond with the nitrate in the solution. Point is, the concentration of the electrolyte, which silver nitrate, silver fluoride, silver whatever, remains the same. What's the suitable answer? Remember, we want to keep our answer brief. So what I said was quite long and very explicit. Well, the rate of oxidation equals the rate of reduction. Boom, bada, ba. We go back there. I'll leave that answer up there for you. The rate of oxidation equals the rate of reduction. Okay, 9.5, write down the balanced equation of the half reaction that takes place at the silver electrode. Okay, so obviously it's been oxidized. Okay, so we just go find the silver half reaction, and it's easiest, I think, to find it on table 4a, because reduction is usually further on top. There we go. So, but we're going to write it the oxidation way. Ag goes to Ag plus 1 electron there. Question 6, the chemical equilibrium section question. It's either question 6 or 7, depending on the exam structure. Okay, sometimes it's an extra question, maybe on a certain section. But here, question 6, the dissociation of iodine molecules to iodine atoms is reversible, and it's a reversible reaction taking place in a sealed container at 727 degrees Celsius. The balanced equation for the reaction is I2 gas goes to 2I gas, okay, which is just iodine atoms. Okay, molecule, 2 bonded together, 1 atom. The Kc for the reaction at 700, or the chemical equilibrium constant, is at 727 degrees Celsius, is 3.76 times 10 to the negative 3. Write down the meaning of the term reversible reaction. Okay, well, that's pretty straightforward, I think, for question 6. Let me just scroll to the top here. All right, for question 6, it's basically that products can be converted back to reactants. Spell that properly. Back to reactants. Okay, short, sweet, precise, correct. 6.2. At equilibrium, the pressure of the system is increased by decreasing the volume of the container at constant temperature. How will each of the following be affected? Choose from increases, decreases, or remains the same. For 6.2.1, the value of the equilibrium constant. If the pressure of the system is increased by decreasing the value, what will happen to the value of the equilibrium constant? Well, for 6.2.1, should be no change. Right? The value will stay the same no matter if the pressure is decreased, or is it increased? Oh, sorry, increased by decreasing the volume of the container. Okay? Nothing will happen. 6.2.2 was what happens if the number of the number of iodine molecules if the pressure of the system is increased by decreasing the volume, right, at constant temperature. Okay, well, it'll definitely be an increase in the number of iodine molecules. Okay, and how do we explain that for question 6.3, which asks us to explain our answer in 6.2.2? And we need to refer to Le Chatelier's principle. Okay, so please make sure when it comes to chemical equilibrium that we do learn Le Chatelier's principle, please. Okay, so Le Chatelier's basically says that, well, explaining it using Le Chatelier's is that when pressure is increased, okay, the reaction that leads to the smaller amount of gas okay, or maybe the smaller amount or smaller number of moles is favored. Okay, so the Chatelier basically looks at the opposite. Instead of favoring the forward, it's going to now favor the reverse. So the reverse reaction is favored. Okay, So when pressures increase, the reaction that leads to the smaller amount of gas or the side with less molecules, or the number of moles, or smaller number of moles, that reaction would be favored. So the reverse reaction is favored in this case. And that's Uncle Le Chatelier. Okay. Don't say Uncle Le Chatelier in your question paper, please. I do not want to be held responsible for that. Okay, that's just me playing around a little bit. 6.4 though, that's where things start heating up and get a little interesting. 6.4, at 227 degrees Celsius, the Kc value for the reaction above increases to 5,6 times 10 to the negative 12. Well, actually, that's not an increase. That's times 10 to the negative 12. That looks like it's actually a decrease. Yeah. Is the forward reaction endothermic or exothermic? Fully explain your answer for 4 marks. Okay. So, 6.4, you can explain it either 2 ways. First of all, it is endothermic. Okay. Now, we can explain it in 1 of 2 ways. We can either explain, first of all, we know it's a decrease. Okay. So, we can either explain it for the decrease in temperature or for the increase in temperature first. Okay. So, I'm going to write it in point form to say that Kc decreases with a decrease in temperature. Okay, you would write this in paragraph form, full sentences form. I'm just going to put the points down here. So it decreases with a decrease of temperature. Now, if that is the case, then the reverse reaction would be favored. Okay, the reverse reaction is favored. Okay, the concentration of the products decreases if this is the case. Okay, so when there's a decrease in the temperature, the Kc value decreases, the reverse reaction would be favored, and the concentration of the products therefore would decrease. Take this point away, make it 1 point. Okay, to cap it off, the decrease in temperature, okay, the decrease in temperature favors an exothermic reaction. Okay, the decrease in temperature favors an exothermic reaction. We could explain it the opposite way, that obviously a Kc calculation or Kc value increases with temperature. If there's an increase in temperature, sorry. So the value of Kc will increase if there is an increase in the temperature. If that is the case, no longer will the reverse reaction be favored, but the forward reaction will be favored. Okay? Now the forward reaction we know is endothermic. Okay? If there's an increase in temperature and the Kc value also increases, the concentration of the products would increase and the concentration of the reactants would decrease. Okay? If in our explanation that we have here, the reverse reaction is favored when there's a decrease in temperature, decrease in the Kc value with a decrease in temperature, the concentration of the products would decrease, but the concentration of the reactants would increase. Okay. But with the increase in temperature, the forward reaction would be favored, meaning the concentration of our reactants would decrease, but the concentration of our products would increase. Okay? If you increase the temperature, all right, it will favor the endothermic reaction. Okay, so the forward reaction is indeed endothermic, the forward reaction. Okay, but we know we had a decrease in temperature, so the reverse obviously would be favored, which is exothermic. Okay, and that was 6.4. All right, let's see what 6.5 has to offer. I'm going to need a clean page. 6.5. A certain mass of iodine molecules is sealed in a 12.3 decimeter cube flask. at a temperature of 727 degrees with the Kc value equaling such. Alright. When equilibrium is reached, the concentration of iodine atoms is found to be 4,79 times 10 to the negative 3 mole per decimeter cubed. Alright. Cool. Calculate the initial mass of iodine molecules in the flask. Okay, alright, I see what's happening here. Well, I think I see what's happening here. Alrighty, let's see. Well, first things first that we need to do, okay, deciding how we're going to do this, is we are given the Kc value, so that's fine when we get to the calculation, but we first need to set up a table, okay? So I'm going to set up a table, and for 6.5. Okay, I'll draw this in real time so we can all see what I'm doing. Okay, cool. You can structure tables like this as well. So I'll write in a different color for now. Let's keep it initial mole. Right, initial mole. So I'll just say initial N, or Ni could be initial mole, however you want to do it. So this is how I'll just do it how I did it when I was at high school. Okay, I said Ni, drew a little line like that. Then I said the change in the amount of moles, Ni. There we go. And let's see, quantity at equilibrium. So NEQ, or I would just say at equilibrium, I would just say EQ, because I knew what that was about, so I just went there. Okay, let me just draw this further down a little bit. And then to cap it off, this was concentration. And I just put concentration there. Okay, cool. Let's maybe extend these lines slightly so we can have enough space for all. Okay, and on top I would just state the substances. So here we only had I2 and I, so we actually have enough space to write in all our values here. Okay, cool. So for the initial amount of moles, I'll say that's unknown, so I'll leave it as, what color am I using? Let's use a different color. Let's use maybe green or red. I'll leave it as X, and this was 0 because I don't know. I'm going to find out the amount of moles. I will find out. Let me see. Let me see. Okay. Actually, let me not do that. Let me actually just leave it blank for now. Actually, just leave it blank for now. Okay, cool. I'm gonna leave it blank for now. I'll show you how it all works out. Okay, cool. So we were told that the concentration of iodine atoms was 4,79. So we can write that in 4,79 times 10 to the power of minus 3 mole per decimeter cube. So we just write down that as an option there. Also, we want to find out now, how do we find out the amount of, or the concentration of I2? Okay, well, that's actually a very simple calculation. We were given that Kc, what the Kc value was. So we know Kc is equal to products over reactants, the concentration of products over the concentration of reactants. Okay, there you go. So we know what the first one was. It was the Kc value 3,76 times 10 to the power of negative 3 is all equal to 4,79 times 10 to the power of minus 3 on top, all squared. Okay, and we're looking for, of course, the concentration of I2 or iodine molecules. Therefore, once we do some equation rearrangement, we'll get what it's equal to. So we'll get this whole thing on top, 4.79 times 10 to the minus 3, all squared, divided by 3.76 times 10 to the power of minus 3. We'll get 6,102 times 10 to the power of negative 3 mole per decimeter cubed. Okay, now that we got that, we can substitute that in this equation. So we got 6,102 times 10 to the minus 3 moles per decimeter cube. Okay, now that we got that, okay, it's a matter of just timesing our concentration by the volume to get the moles, because we work out concentration by equilibrium mole. Okay, so this is N at equilibrium, just to put it in there. So obviously, if we take our concentration and we multiply it by the volume, which was 12.3, okay, so I'm going to write it in another color just for explanation purposes, times by 12.3, we'll get obviously what the equilibrium mole is equal to, okay, which I'll write in this color. Okay, so we should get that the equilibrium mole, if you times it there by 12.3, let's just actually do that. So 4.79 times 10 to the power of negative 3 multiplied by 12.3. So the equilibrium mole of iodine atoms is 0.0589. And that will be the same for the change because there is nothing over there. And we'll take the same one for 6,102 times 10 to the negative 3. We actually get 0.0751.
And then, JP, then you use the mole ratio.
Sorry, everybody, I'm being a bit foolish. I forgot that the balancing number here was 2. It's 2i. So I had to use the mole ratio actually just to say 0.0589 just divided by 2 times 1. This would give you 0.0295. All right, there we go. 0.0295. And then if I take 0.0751, so now the change in equilibrium, so what you get to get your change, I think you take your initial minus what that was used up to get how much actually reacted. So to get your equilibrium mole, you just multiply. Oh, not multiply, sorry. You add these two answers together to get what you had initially. Okay, so that should give you 0.104. And if you use these rounded up answers, then you will get 0.1046. All right, if you use these rounded up answers. Okay, so initially I think that 0.61 or 6.102, just get that on my calculator because I think I still have that. You would have had 0.7505 blah blah blah. So if you take that whole answer, okay, and you add 0.0589 divided by 2 to get that whole answer, you'll get 0.1045. But because we use these answers, we get a 0.1046. So if you got 0.1045 here, it's also okay. I just use these answers here, so that's how I got that. So now that you got your initial mole, obviously what you can do is you can substitute that into your mass equals mole times the molar mass. Okay, so because that's what we're looking for, the initial mass of iodine molecules. So now therefore N is equal to M over big M. Then for the mass is equal to M times big M. So 0.1046 as my answer. If you got 0.1045, it's still correct. The molar mass of iodine molecules, I think, is 254. I want to double check that on my periodic table quickly. Just find iodine. Yeah, so that's 120 Yeah. So in some periodic tables, depending, this in the textbook I'm using 126.9. So I would have got 253.8. But in think the periodic table that they give you whole numbers. So that should be 254. We should get an answer 0.1046 times 254 of 26.5. It must be to 2 decimal places. So 26.57. I got 26.5684. Let me write that down for everybody. 5684 to 2 decimal places. Therefore, the mass should equal should equal 26.57 grams. To maybe end off things with question 4, sometimes also can become a trickier question in paper 2, and we basically just went through some of the major questions. Question 3, question 5 is not as major, but I believe that everybody is capable of doing those questions by just good enough study. But question 4 can get a bit complicated. Obviously got explaining a flow chart here of certain types of reactions happening with organic compounds. And 4.1 asks us to write down the meaning of hydrohalogenation. Okay, question that's not often seen. Okay, but for question 4, for this one, I think we can all see this color. I'll change color soon, sorry. 4.1, hydrohalogenation, it is the addition of a hydrogen halide, okay, or a halogen bonded to a hydrogen halide to an alkene. That is the correct definition for it. All right, adding a hydrogen halide to an alkene. Okay, let's switch color quickly. 4.2, okay, also I think for structural formula, let me write down the structural formula of compound Q. So we've got compound P, reaction 1 takes place, but compound Q, bromination takes place and goes to compound R, and compound P, they say, is a starting agent. Various organic compounds can be prepared using compound P as a starting agent, so that we get compound Q. Also 4.3 helps us a little bit with 4.2. It says that reaction 1 is an elimination reaction. Okay, so compound Q, if bromination is going to take place to form compound R, then compound Q should be an alkene. And let's see what else helps us with the question. So we've got an alkene there, plus C5H12, and there's hydrohalogenation comes down here. 1, 2, 3, 4. That looks like it might be a methyl on there. CH3, CHCl, CH3. Oh no, sorry, it's 1, 2, 3. That's chlorine. Sorry, I counted the C in chlorine as carbon. 1, 2, 3. So that should help us with compound Q. So it's definitely 3 carbons. 1, 2, 3. The definition for hydrohalogenation is that it must be an addition of a hydrogen halide to an alkene. So we know it's an alkene, and it looks like the position of chlorine, so that's going to be the first carbon. So I'm definitely going to make the double bond here. Make that a bit of a straight line, okay. And then let's add the hydrogen halide, hydrogens in here. H, 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 H. Hope that makes sense. 4.3. Reaction 1 is an elimination reaction. Okay, great. So write down the type of elimination reaction. So we're breaking up something to get an alkene. Okay, so that elimination reaction is cracking. Okay, that's cracking. And 4.3.2 asks us for the molecular formula of compound P. Okay, so compound P for 4.3.2 is 1,2-dibromo Okay, propane. Okay, there is a space there. 1,2-dibromopropane. Okay, it's an elimination reaction. Okay, to get compound Q, which we obviously deduced from this, going backwards, getting rid of the hydrogen and the chlorine. Get an alkene, and then it also undergoes bromination to get compound R. All right, for 4.4. Oh my word, no, sorry, I wrote down the bromination one too soon. I wrote down 4.4's answer. I totally messed that up, probably because I've been sitting at the screen for so long. Sorry, that was 4.4's question. They asked for the molecular formula of compound P, sorry, so that's actually C8H18. The reason being is because we get a compound there and C5H12. So we've got C5H12 in the cracking process, you're splitting up, okay, into an alkene, all right, or you're cracking an alkane rather. So if you've got that, then that means C5H12. That should also help you to realize, okay, cool, well, the compound Q we already realized had 3 carbons, therefore compound P had to have 8 carbons, and then just add the hydrogens back. Okay, let's just check how many hydrogens I have. 1, 2, 3, 4, 5, and 6. Okay, there we go. C5H12, compound Q, 6, bring it all together, C8, H18. Okay, 4.4's answer I just gave, but I'm going to give it again. Just read the question. I think it was write down the IUPAC name of compound R. So compound R undergoes a special also undergoes halogenation. So you're adding the bromines to it, so it's called bromination. So you're adding 2,1,2 dibromo propane. We know it's propane because compound Q has 3 carbons. Propane, sorry. Okay, and 4.5, I think was the last question. You just see 4.5 for 1 and 4.5.2. Okay, to end off quickly, for the hydrolysis reaction, okay, which is the hydrohalogenation compound going to compound S, write down the balanced equation using structural formulae, okay, to get compound S. Okay, so let's do that for 4.5.1. So, of course, we've got, okay, and on the second one, we've got the chlorine. And I'm going to leave these other branches blank for now because I don't want to waste time putting in the hydrogen. Okay, now hydrolysis, we've got to react it with a strong base with the presence of OH. So we can either react it with sodium or sodium hydroxide, water, or potassium hydroxide. Okay, I'm going to write water, H2O. And that should give us, of course, that stays the same. Second one. Now we've got the hydroxyl group present here now. Okay, and everything else stays the same. Plus, we've got another compound, but I'm going to write that plus at the bottom here. Plus, of course, we've got water, so that goes HCl. If you use sodium hydroxide, that would be NaCl. If you use potassium hydroxide, it would be KCl. But we used water, so it's HCl, which is hydrochloric acid. So we get an alcohol plus an acid for 4.5.1. Okay. 4.5.2, which is the final question for this question and for the session. 2 conditions for hydrolysis. Okay. Well, needs to be heat, but mild heat, okay, and must be a dilute strong base needed to cause hydrolysis to take place. Dilute strong base, okay, or water. So we can say or water because we used water and it worked. Okay, for the 2 reaction conditions. Okay, and that wraps up all that we had time for on this Saturday to go through for the question. And that was 15 marks for this question. So it wasn't the easiest one of all, but it actually wasn't even that bad of a flowchart, to be honest. And that grade 12s brings us to an end for paper 2 revision before the exam on the 15th of November 2021. It's been a pleasure tutoring you all, for those present in my class and those watching the online videos as well on the channel. Good, better, best online videos. It's been fun. Wishing you all the best for paper 2, and anyone else that watches this video in the future, all the best for your exams as well, because you too can benefit from this tutorial as well. Take care, and as I always say, we'll catch you in the next one.